Good afternoon. Thank you for joining me today. My name is Hendrix Mortimore. I'm an engineer in the Design and Simulation Department at the National Composites Centre in the UK. Today, I'll be taking you through our braiding simulation workflow for composite materials and how we use braiding simulation to drive the design process. The National Composites Centre was established back in 2011 to support the delivery of the UK composite strategy. The function of the NCC is to bridge the gap between academia and production, where we take innovative ideas and use our expertise to develop them into future products for industry. Our focus is on bridging the valley of death. This is working within technology readiness levels 4 to 6. This is across applied research and development. The company works with a number of OEMs and across a wide range of sectors, including renewables, public transport, energy, automotive, and aerospace. So what is braiding? Braiding is a unique technology which has the capability of producing high volume yet low cost composite components. With the reinforcement as a 3D woven fabric, complex shapes can be easily manufactured inexpensively due to the high deposition rate and the automation. The method used to create the braid is that fibers are loaded onto two sets of bobbins on the which are then loaded into the outer ring of the machine. These two sets of bobbins then rotate in two concentric orbits opposing each other as a mold moves through the machine. This process creates a helical fiber path which can be tailored to the component structure requirements. This is an overview of the design process the NCC goes through when developing a component or a system. The first stage is going through the requirements capture, interfacing with the customer to use that information to then drive the design process. This leads on to concept generation, where we create multiple designs, potential solutions, which are then filtered down and scored against our requirements. Following this then comes the detailed design analysis and finally the optimization of the component. And this is where CBX slots into the process. So CBX is a CATIA workbench dedicated to composite braiding design. The software is a powerful 3D braiding process application, which allows designers to accelerate the design of braided components. The braiding simulation allows designers to visualize the fiber paths on complex components and optimize machine parameters to achieve desired fiber orientations prior to manufacturing. So what are the key parameters to braiding? So braiding is an automated process, and the performance characteristics of the laminate are determined by the machine parameters. This is not an exhaustive list of all the parameters, but these are the primary ones. There's the bobbin carrier speed. This is in which the bobbins travel around the machine in the orbital path. So the faster the bobbin moves around the component, the more material you can deposit, but then that creates a higher fiber angle. There's also the feed rate, which is how fast the component moves through the machine. Again, this affects the braid angle. So if a part moves at half the speed, you can wrap around twice as much fiber over the same unit of length. There's also the number of fibers used per layer, the ratio between those fibers, and the fiber material itself. There's also the spring tension, which is the force the fibers are pulled onto the mandrel, the guide ring size, and also the orientation of the part within the guide ring. So, to demonstrate the capability of braiding, we've selected a propeller blade as the showcase component. The challenge with this component is creating a quality part while being able to manufacture the aerodynamic shape of the blade. This has a variable cross-section, particularly from the root of the blade where it's held in the clasp to the actual body, which this has a direct effect on the fiber architecture and the quality of the final component. So why braid a propeller with these challenges? Well, the process creates damage-tolerant structures due to the interleaved nature of the fibers, which is a key performance criteria to impact load cases for while in use. Furthermore, the process is ideal for high volume production to meet market demand. So, running all these simulations, how have we built confidence that we know what we output is correct? So the NCC has gone through a number of empirical studies using a range of geometries and braid architectures to test and verify our virtual data with manufacturing. Specifically for this component, we designed, analyzed, and braided a subscale airfoil geometry. The output fiber angle and layer thickness were directly compared to the laminate data created by CBX. This test and verification and the positive results we gathered from this enable us to have confidence when we took the design to the more complex stage. CBX creates a virtual environment in which you can set the braid machine parameters and rapidly output laminate data such as thickness, fiber angle, and cover factor. So through this, you can fine-tune your input parameters to assess the feasibility at preliminary design stage. So you look at how the part braids, where you can highlight any manufacturing problems early on, or you can also use that to then optimize the final the braid architecture on the part before it goes to manufacture. The key parameters specifically for the propeller are the braid path, so you need to adjust for the cross-sectional change, particularly when moving from the root to the body of the blade. There's also the mandrel versus the carrier speed, which determines the biaxial fiber angle, and also the fibers used in the laminate. Combining these factors, you can regulate the braid output to maximize the mechanical performance. Now we understand the parameters. This is the difference between a simple part and an optimized one. Propeller blades in operation are mostly under tension, in which with a small component of bending. So the key to maximizing the performance of the blade is to control the axial fibers, these are the ones that run along the length of the blade, to be in line with the load path, while also maintaining a balanced laminate to not have any weird failure modes. You can clearly see the difference in the quality between the initial one and the optimized component here. One of the brilliant features from CBX is the ability to output the laminate data into a finite element solver. So CBX can, after it's created the kinematic drape, can mesh the part and apply the material data created in the kinematic drape onto the mesh, such as the element thickness and the fiber orientation. The data generated allows the designer early on to create FE models, assess structural performance, and also run optimization routines against known load cases. This is a really powerful tool because in progressing the part design, as you can design in the virtual space and create laminates, opposed to a estimate, manufacture, test, and then iterate approach. To summarize, we've gone through the braiding simulation workflow, starting with the requirements and working through to a final component. Utilizing the software packages we have available, we have been able to improve our capability of these advantages. Design efficiency. We're able to run manufacturing assessments and use simulation-driven decisions from the start of the design process. Quick and effective model generation. We have the ability to quickly create and generate kinematic drape data and modify that very easily, and then use that to feed into our structural analysis models. Process-driven design. When designing a braided component, the process design drives a lot of the design process, and being able to refine a component and assess it in the virtual space is a really powerful tool. And then you also have the capability to preliminarily look at the feasibility of a component. So braiding is a fantastic process, but it's not for everything. And being able to look at a component and assess at a very early stage, that you can look at the manufacturing limitations and decide whether it's a suitable solution or not. Thank you for listening, and if you have any questions, please don't hesitate to contact me on the email below.